Do I need to tell you why this work is important? Actually, if it was in November or December last year, maybe you're going to tell me, okay, we know about flood. We know that it's important in New Zealand. But I think that now, after what happened in January, Auckland anniversary, and in February, Cyclone Gabrielle, I think we do understand now, and I don't have to explain you why. So I will directly skip that context and tell you exactly, to give you a bit of understanding why we are doing this job. I would like to put you in the shoes of a flood forecaster at a regional council, what is doing right now to assess the risk of flooding when it happened in the Waikato region. So we have the guy in the middle here, which is the flood officer. It received information from the weather forecast from Met Service, which is the official weather provider in New Zealand. And it will get information from the council, which is the organization in New Zealand for keeping their eyes on rivers. So river level, river flow, everything about it's related to rivers. It's get all the information. It got some river level station over the region. And it will manage to understand the risk just by getting these two information. And the output of his analysis to this person, which is going to be delivered to all local emergency management team, district council, it could be communities, Mourot, about the potential risk in their area. It will also describe everything into some sort of a report, and he will put as much as information as he can on a website. And for the Waikato region, there is this flood monitoring room, which tell everybody about latest information the council have to manage the current situation. It's very simple. What we would like to do is getting more about analysis in real time here when we need it. Okay. So the question about flood prediction, this is what we have been working on last year. But now we are really focusing on, we've got a model, we've got something running which is predicting very well, and I will let my colleague to speak about it. But how we can really deploy a model into real life situation. So just to give you a bit of an idea about traditional approach, which is like we are collecting data, we're trying to save them in somewhere, and we do some processing, and then we've got something in on the output, some prediction, something that we can provide to people that need it. But it came to a limit where we get too much information, when the information coming from different sources is gonna get tricky, and then it put a lot of struggling into the process. So where we are aiming at is having some sort of a framework that could collect as much as data as possible, and you know that data is the fuel for AI. And then we can also run different type of model from different sources as well. We can update as well, as you know, a model, we really have to update it at different time. And then we can provide maybe different type of information to different type of users. Okay, and this is what Albert was talking about. We really want to embrace the data mesh framework, because I think this is a solution to decentralize the storage of the data and to be able to handle much more data in real time. So I will let my colleague to have a look at the engine.
All right. So this year has been a really exciting time for machine learning. So many of you have heard of ChatGPT, and this pretty much have been the #1 application for basically machine learning and AI well known to the public, and very similar to predicting is a sequence of words that follow from a language model. what we call predicting the river levels is also something that's very related to the task that we call ChatGPT is trying to do. So the underlying technology behind ChatGPT or these large language models is a technology is a AI algorithm called transformers. So over the last year, we've been exploring about looking to transformers to see how well it can work on to predict what call river levels and to try to improve the accuracy and the forecast horizon of our flood prediction models. So there is a bit of a mixed bag. One challenge that to do with transformers is that transformers can be very data hungry. In the case of ChatGPT, it was trained on pretty much the whole corpus of Wikipedia and other texts that are available. Let's say so. Transformers requires a lot of data to train, and there is a challenge to say, well, how can we improve the quality of the model using with just the limited data that we have from the historical river levels and rain radar. So right off the bat, the transformers itself, the native transformers did perform all right, but it's not comparable to our baseline model. One of the few things that we notice is that the transformers tend to give noisier predictions, and then it tends to be a bit more conservative. It tends to give what we call the average prediction. So things that it doesn't predict the peaks and the peaks and the valleys of the river levels well. However, there is other variants of the transformers. One of the variant that works really well is one called ETS-former. This is a transformer that was called tailor-made for time series prediction. So here you can see that it gives a nice it seems to predict really well with the rise and fall, but then it still has some jittering or inconsistency, things that we need to basically address in the prediction, especially during the falling edges of the transformers. There are other works that we are trying to look into working on these transformers as well. One is basically trying to understand how these transformers works, how to get the predictive interval, because if you were to give a prediction, we need to know how confident it is for the machine learning algorithm is on that prediction, and what are the ranges of the prediction that might be possible in that they think is possible for the river levels, and that will basically help give the flood officers a good gauge of what they think the risks are for the flooding risks are for the short term. The other work that we have also looked at is increasing the area of the rain radar area of that we integrated into the forecast. So over the last year, we have worked very closely with Met Service, and they have exposed the rain radar archives for us to make use of. And using that, we are able to extract out a larger area of the rain radar from the Met Service, and basically use that larger area, the larger service area of the rain radar for the prediction. For the record, the previous system we've been using was just about 150 kilometers by 100 kilometers, but the clouds and the rain clouds that are flowing through, they say flies over at somewhere between 50 kilometers to 80 kilometers per hour. So that 100 kilometers radius is barely 2 hours of future clouds coverage that are available. So by increasing the cloud horizon, we are able to improve the forecast window, but there comes a trade-off in the stability of the predictions so this is an ongoing work that we are trying to improve on and something that we will address. We will hopefully get some good updates for next year. So we also been working on the new dashboard for the flood prediction system. So right now, we're going to have with the ideas here, we're going to have an overview of the status of the rivers over the their being serviced. We are going to have a forecast horizon. The forecast of the river. The green part is the historical values, and the red line, the black lines are the forecasted value with its predictive intervals. And so at the bottom, we're going to display what the historical rain levels are for two different rain gauges. And on the left side of that rain gauges, we're going to display the cloud coverage. Running a bit low on time, so I won't actually show the video here, but we actually have a video link that can share with guys later. Sorry. All right, it's insisting to display the video. Here, swap between rivers and view the status of the rivers and see the different time frames. All right. So behind the scene, we are basically working with Met Service and the Waikato Regional Council, and we're getting the data from them, and to train the neural network model. And then finally, we're gonna have the visualization server that's deployed on the clouds. So for public consumption. All right, sir. All right. So I'll pass the time on to Corey, which will.
Thank you, Nick.
Thank you.
So I want to talk about islands of research. So like Nick's flood prediction work, he's come up with some amazing results. I'm sure we're going to see a lot more here today. But how do other people access these? So we have the TAIAO web platform that we saw at the beginning, and that's great. You can access some data sets that people have put up there, see some code. But what we also need, in addition to that, is a place for living data sets and evolving models, so things that update in real time. So what I'm working on is the TAIAO cloud platform, as opposed to the web platform. So that's hosting Nick's flood prediction on the prototype right now. And it's a cloud platform with GPU support for training and running inference on models, but also for storing data sets and updating them and providing web visualizations and APIs that people can access. So just quickly, some details. The platform runs a function as a unit, which I'm calling a service. It just runs code that reads new data, polls for new data, does some processing and outputs it. Each service gets a dedicated storage for its output data, but also stores its state. So if it needs to restart, it can pick up where it left off. And it gets GPU support and can also provide web accessible endpoint. Sorry, I'm going quite fast because I'm not sure how much time I have left.
You got 5.
Okay. So how can people use it? We currently only support Python and prototype, but that may expand later. So basically, pip install a library, which gives you the tools you need to develop a service. You write a Python script, which defines the function to run as your service. And then you call a setup function, which describes your service to the platform. And then you submit that along with any static data files, and the platform will upload it and run it. So we've got an example here. I'll just go through that quickly. So I'm using a typed version. So I'm just defining my type of my state and my output for my service. And then the function takes the previous state and output if it's not the first time it's running, so it can restart, and then an emit function, so it can emit new states and output. And then this is the setup function describing some naming and giving the body of the service plus requirements that it needs, and describing whether it should run periodically and whether it should provide a endpoint for network access. I'll skip over this. Suffice to say, there is a deployment process that analyzes that and deploys it to the platform. The technologies we're using is Kubernetes for resource allocation, so assigning your service to a machine in the cloud, and Kafka for data persistence. And then we're running it on a hybrid cloud using public AWS at the moment, and on-premise machine for GPU support. Challenges that the platform will face is obviously security, running arbitrary user code, and have to make sure it's safe for the platform and safe for other tenants on the platform. Resource allocation, so making sure that services get the GPU use and disk usage and stuff like that that they need without taking it away from other services. Reliability, so not only keeping the service running continuously, but also providing tools so that people developing these services can fix any errors that might come up or things like that. And then just providing a good developer experience, so it's easy to convert your experimental code into something that runs live on the cloud. And so the future work for the platform, it's in prototype at the moment, so getting towards a release, being able to change services while they're running, shared protocol definition. So if you have one service that needs to read data from another service, making sure they both understand what that data should look like. Migration management, so if you need to update a service, how do we make sure that data previously written by that service is still usable? And then working towards high performance parallel tasks, client code privacy, and support for other languages, including compile programs. And that's it. I don't have any insight.
Thank you. I just wanted to, before your claps, we forget to present Corey, which is developer in the and especially war engineer, data engineer. I think that's quite some sort of
research program is
research program
job title.
And of course, Nick working for this amazing flood prediction project. So no, you can. Thank you. Very good. Oh, you've got question. I'm not sure if we have time every time for question, because so sorry, but we're spending all the day, so I will get off every question. We are allowed to question. Okay, two. Number one.
So it's very prototype at the moment. I've just released the library privately to a few colleagues for them to start working with prototypes. There's no public documentation yet.
But it will be, I think.
Yeah, that's definitely something we're working towards. The security of the platform is the next thing that needs like a really strong audit before anything becomes publicly available.
You've got an yep.
I think that might be a question for you, Nick.
Do you mean that this working in real time for flood prediction? That's why. Yeah, this is exactly the purpose, and this is exactly the purpose of this framework. Actually, we don't have to retrieve the data, do the processing, and provide an output. So this is a prediction. The way that this framework's working is we have a flow of data coming, and then we've got this models running in real time on every time we've got a new data. and then we provide in real time again a prediction. So of course we are not talking about seconds, because we don't have any new data every second. And I think that, for instance, the regional council provided a data every 5 minutes, and then we can have the radar, mid-service radar every
7.5 minutes.
7.5 minutes.
Yeah.
So yeah.
There is a slight delay between the uploads from the when it's generated and saying, so we have to take in consideration the lag of the uploads and the frequency of that. But overall, we expect to get the data at least 30. There should be about 30 minutes lag between the latest data and before a new batch of data comes in.
Totally. So it's exactly the purpose of this new kind of approach for running such model like this in real time for real life problem. Yeah.
Can I just add to that as well? So it's very general. So for collecting data, a service could be an endpoint that a sensor pushes data to. It could be something that continuously is polling for data from a source. It could be running a web server where someone has to manually drag and drop a CSV file into it. There's a lot of flexibility there in how data can be collected.
Mm-hmm. Mm-hmm. Yeah, this is something that we got that is in our plans to address. So currently we've been working so far with historical data and clean historical data, which might not to actually represent what called the real situations. So some of the things that we're going to consider is what happens when some sensors are not available. How do we fall back onto a less accurate but less reliable model, but still give a good prediction. So these are the things that we are sort of considering. We're trying to consider also include into our platform to basically have fallback systems and working on the aggregates of the predictions to give us something that's reliable.
Thank you. Awesome. I would like to welcome the next project speakers for Flow. Thank you, Nick and Corey.